Okay. All right. So the other day we started talking about transformers, and I want to do a couple of examples of those today. We didn't get to do any examples on Friday in class. So we'll begin with that today. Um, so what we talked about basically is the way that transformers sort of work and the rationale for them. So this is sort of a high level picture, at least, of what one looks like, where typically we have a voltage source on one side and then some set of loads on the other side. And we typically call the side with the load the primary. And then we think of the side with the side with the source as the primary and the side with the load as the secondary. And what we talked about is basically if I have a magnetic field from one set of coils that causes a magnetic field to go through another coil, as long as that field is changing with respect to time, then what that field will do is to induce a voltage in the other side. And so we typically use this to step voltages up and down in a system. We also often use it for kind of isolating different parts of a circuit. What I mean by that, I don't really talk about that too much, but basically these two sides of the circuit can effectively be grounded differently. The primary and secondary could. But the way we typically do this is we have a piece of iron that basically makes sure that the magnetic field that is created by the current in the primary, all of that magnetic field makes it to the secondary, or at least almost all of it makes it to the secondary. So the job of that iron is to direct the magnetic field. Now, where we kind of ended on Friday is we talked about sort of the way that this thing is treated in circuits. And so we typically use this picture right here for what we call an ideal transformer. And that's the only thing we're going to deal with in this class is ideal transformers. We're not going to deal with a quote unquote real transformer, which is to say that it has some imperfections and maybe some of the magnetic field doesn't reach the other coil. Those factors we're going to sort of abstract away. We're going to assume that it's ideal. So the important thing is that this is our circuit element that we draw in our schematics. These are not two inductors. This is an ideal transformer. When we see this, basically those two inductors with the lines between them and these dots, that implies that we have an ideal transformer. So there's no inductance that's associated necessarily with either of those two coils. All right, we're not going to treat them that way in our problems, as we'll see. What I've defined here is basically saying that there's a voltage on the primary side, typically is 1 is the primary side, and the subscript 2 is used for the secondary side. And we have a turns ratio, which is the ratio of the number of turns on the two sides. And what we talked about is that the number of turns controls the voltage transformation and current transformation ratios. So I showed and derived a little bit in the notes that I posted this relationship here, which is to say that the voltage on the primary divided by the number of turns on the primary is equal to the voltage on the secondary divided by the number of turns on the secondary. So V1 over N1 equals V2 over N2. Now, what we said is we have this dot convention. And what this deals with is basically the ways in which the transformer is wound, the directionality of the windings, because that affects some things about how the magnetic fields behave. So I'm not going to get into the nitty-gritty details of all that sort of stuff. But I did want to say basically this relationship is positive, where both sides of that equation are positive if the plus terminal of the voltages are either both at the dot or both not at the dot. So if one of the voltages is reversed, then you put a negative sign in there. So what that means is that for this particular case here, I would have V1 over N1 equals V2 over N2, because the plus sign on the voltages is at the dot, right? If I had, let's say, this picture, let's say a dot here, call that V1, and a dot here, call that V2, right? This particular instance would be V1 over N1 equals negative V2 over N2, all right? So if we do them differently, right? If it's a mix of where the plus sign is, then there's a negative. All right. So that's an important thing that we'll use in our analysis. And this is kind of like passive sign convention sort of stuff. It's not too particularly challenging to get your head around it. But it is just a piece that we need to kind of understand in dealing with these things. Now, the thing that I dealt with the other day is I said, okay, well, if I've got a situation like I have here, so I've derived, that voltage relationship here. So V1 over N1 equals V2 over N2, right? What I can do is I can get the power relationship. And I always suggest that the total power into this thing, P1 plus P2, has to be equal to 0. That's because if it's ideal, there's no losses in this thing. And what I did was I used the passive sign convention to write that the power on the primary side is V times I, and on the other side is V times I. Now, real quick, if I had so you guys probably don't remember this too much because you don't think about it too much after the very beginning of circuits 1. But if I have this relationship where I is flowing into the plus sign, this particular case, I say that power is V1 I1. But if the current was flowing the opposite direction, then it would be the negative of that. In other words, power would be leaving. This basically implies that power is entering. If the current is going out, we would write the power as negative. And that would be a situation where we would say that the power is leaving the device. Okay. So we're going to deal with that in some examples here in a second, but this relationship basically gives us this relationship here, right? Which can have a minus sign or not, based on however the polarities are drawn in the problem. The important thing that I think of typically is I look at the relationships with the magnitudes. So what I see is that for the voltages, I have this magnitude relationship. For the currents, I have this magnitude relationship. So the way I always think about this is the side with more turns always has more voltage, and the side with fewer turns always has more current. So if there's 4 times the number of turns on one side of a transformer, it has 4 times the voltage and 1/4 the current. But the power on the two sides is the same. Okay, so I'm going to stop there for a second. Any questions up to this point? And we're going to jump into some examples here in a second. No questions. Okay. All right. If you have a question, just jump in with it. No problems with that. All right. So basically, whenever we have these problems, I kind of break it down into sort of a 4-step process. I get the voltage relationship, which is always related as I have here by the magnitude relationships, right? And then I check to see if the sign is positive or negative. In other words, if both plus signs are at the dot, it's positive. If both negative signs are at the dot, it's positive. Otherwise, the sign is negative. Okay, and we'll look at some examples of that. What I then do is say P1 plus P2 equals 0, and I write P1 and P2 using the passive sign convention. From there, I get the current relationship, and then I just do the circuit analysis from there with my KVL, KCL, sort of typical stuff. So that's kind of our typical process. All right, so let's now do an example. So I've got this particular circuit, and I want to solve for a couple of things. I want to solve for V1, V2, I1, and I2. So basically, V1 is the voltage on the primary, V2 is the voltage on the secondary, and then I1 and I2 are the currents. And I've been given the definitions that are here in this particular problem. Okay, so the first step, all right, how should I, given the polarities that I've gotten here, all right, and I'm going to look to you guys to tell me, how should I write the relationship between V1 and V2? So notice that this guy is 4 to 1. So that basically means that N1 equals 4 and N2 equals 1. How would I write that relationship given what we have here? What would I do?
So V1 over N1 is negative V2 over N2.
So in this case, yeah, so V1 over N1 would be V1 over 4. And in this case, it would be positive So V2 over 1, like that. And the reason it's positive is because both of their plus signs are at the dot. All right, so it's a little bit tricky because they're reversed from each other in terms of where they're located on the component, but both the plus signs are located there at the dot. So we would make them positive. That's kind of our definition here is the sign is always positive if they're at the dot. Okay. So
What does the dot mean? Does it represent anything or?
it does. What it means, it refers to how the transformer is wound. So in other words, if I were to look at a transformer, if I look at the picture, it's a great question, right? So the way this guy is set up is if I look at the primary, this guy is going in that direction. I guess that would be a counterclockwise direction that he's wound. I could potentially have wound it in a clockwise direction, in the opposite way. That is what affects the dot. In the way that we kind of determine that typically in my mind is if I put a current into the dot on one side, it will naturally cause a current to flow out of the dot on the other side. All right, but our ways of determining how it affects the relationship, we just kind of go through this process here. But that's a great question. It refers to the winding of it and how it's wound. So without seeing the transformer and how it's wound, it's kind of hard to determine that. So it's usually just something that we're given. This would be where a lab would be useful to sort of understand that for sure. Okay. Any other questions about just how I got to this? Okay. All right. So let's keep going with this. I get to my step 2, which is basically to sum up the powers. So we said P1 plus P2 always has to be equal to 0. So we have also determined for ourselves that V1 over 4 is equal to V2 over N2, which in this case is just simply V2. Now, what I do here is I look at this and I say, well, what would P1 be and what would P2 be? So in this case, given the direction of I1, which is into the plus sign of V1, how would I write P1 by the passive sign convention? In terms of,
Positive.
it'd be positive, yeah. So it'd be V1, I1. And on the other side, if I look at I2 would be going into the plus sign here, okay? So I would say that this is also positive, V2, I2. Now, what I typically do is I then say, okay, well, but I also know that V2 is equal to V1 over 4 in this case. So I make that substitution and I say P1 plus P2 equals 0. And that becomes V1 I1 plus V1 over 4 times I2 equals 0. The V1s cancel out of that because we know V1 is not equal to 0. And we get that I1 has to be equal to negative I2 over 4. All right. So now we have our current relationship. And magnitude-wise, this should make sense. What it tells me is that the voltage on the primary side has to be 4 times the voltage on the secondary. And it's saying that the current on the secondary side has to be 4 times the current on the primary side. All right. So the side with more turns has more voltage. The side with fewer turns has more current. All right. So we can always do kind of a quick check. Any questions about how I got to that?
Yeah. How did the V1 cancel out?
Well, so basically, if I look at this, I got a V1 in both terms here, right? So I can say V1 times I1 plus I2 over 4 equals 0. So I got the product of two things that are equal to 0. V1 should not necessarily ever be equal to 0. So you basically would sort of cancel that out and say I1 plus I2 over 4 must be equal to 0 to make that true. So that's always going to be the case, that mathematical statement is true. It makes sure basically to say that What, I mean, this statement here is basically a statement to say that whatever power is going into one side has to come out of the other side. It's just, that
Okay.
there's no losses inside the transformer.
Okay. All right, thank you.
Yep, good question. All right. All right, so now I get to my third step, which actually I kind of already did, which my third step was to, if I go back to my formulations, to get the current relationship. So that basically was to say that I1 equals negative I2 over 4. Let me see. Okay, I got plenty of space. Okay, and then my other relationship, right? So I1 is negative I2 over 4. And then my other one is that V1 over 4 equals V2. Okay. All right, we're going to use those now in my fourth step, which is to solve this thing. Okay. So what's the approach for solving it? Well, basically what I've got here is two meshes. Right? That's the way that I look at this. One mesh on the left side, on the primary, and one mesh on the secondary. And I'm just going to label this up and say, all right, I got a voltage here, VA, and I got a voltage here, VB, like that. And I'm going to say I got a voltage across the series combination of the 3 plus J2 that I'm going to call V sub C, like that. And I've got defined for myself that I1 is going this direction, and that I2 is going that direction. So I'm going to treat this like it's a regular mesh problem. Okay. So help me out. On the left mesh, I'm going to start here in this corner, and I want to work my way around. So I say 0 equals. In terms of the voltages that I've written there, how would I write this out? What do I do is I go around in I guess a clockwise direction, starting at the 100 volt source. How would I write this?
Negative 100 angles go.
Yep.
Plus VA.
Yep.
Plus V1.
Yep.
Plus VB.
You got it. Okay. That's exactly right. So I'm going to move the 100 over. Oops. I'll move the 100 over. Now I'm going to substitute in for VA and VB. I can't substitute in anything for V1. V1 is an unknown that I don't have a relationship for, so I'm just going to leave it there. But for VA, I clearly have that should be, by the passive sign convention again, I1 times 32 plus J16, like that, right? So VA is the combination, series combination of those two things. And then for VB, that would be I1 times negative J24. All right. And then for V1, again, I don't have anything I know about that one, so I'm just going to call it V1 like that. Now, I do want to point out here, one thing that sometimes confuses people is this, when they show these capacitors, sometimes there's that, the side that is flat and then the side that's rounded. That has some implications, I guess, in terms of actually placing a capacitor in a circuit. But it doesn't mean anything. It doesn't mean that I need to define the flat side as positive and the curvy side as negative. I can define it however I want, and I did that here. All right. So what I wrote there is totally fine. I could have, if I wanted to, made the flat side positive and the curvy side negative, but I would have to do some things differently in writing my passive sign convention. There is no reason why you have to choose any one of those two sides to be positive, though, and that's kind of the important point. All right. This equation is basically here, satisfies the passive sign convention as I've got it. So what I do is I'm going to simplify this guy, and I'm going to say that I have I1 times 32, let's see, plus J16 minus J24, so this becomes minus J8, like that, plus V1. Okay, so that's one equation. That's the one I get from the left mesh that I've written here. Now I want to do the right mesh. Right, so the right mesh means I'm going to start again in this corner, and I'm going to follow around in the direction of the current that I've written here. So if I do that, how do I approach that as I go around this circuit? How would I write that? Help me out. Where do I begin?
Plus V2
Yep.
plus VC plus
Yep.
the voltage source.
Yep, plus VC plus the voltage source. And the voltage source in this case is 20 angle negative 20 degrees, like that. So for V2, I don't have anything that I can write for it. So I'm going to say I have 0 equals V2. And then for V sub C, right? V sub C is the voltage across that series combination of the 3 ohm and the J2. So that becomes plus I2 times 3 plus J2. And I'm going to move I'm going to say negative 20 angle 20 degrees on this side. Okay. But technically that negative means that I add 180 degrees to the angle. So that's something I probably should do. But I wanted to say, okay, look at this. Now I've got 2 equations and 4 unknowns, right? So my 4 unknowns are I1, V1, V2, and I2. But I could turn that into 2 unknowns, right? How do I turn that into 2 unknowns? What do I need to do to that bottom equation? What do we know about the relationship here between V1 and V2? Well, we know this, right? So we know that V1 over 4 equals V2, and I1 equals negative I2 over 4. So what we do is I'm going to make a replacement. I'm going to say, okay, I2 equals negative 4 I1, like that. And V2 equals V1 over 4. So I'm going to use that in this equation here to say I'm going to have negative 20 angle 20 degrees equals, instead of saying V2, I'm going to say V1. Whoa. I'm going to say this is V1 over 4. And I'm going to say for I2 that it's negative 4 I1 times 3 plus J2. Right? So now I have 2 equations and 2 unknowns. And to solve it, I just need to go through my typical sort of solution process. So I end up with, again, I'm going to write this as, for the first left mesh, I get 100 equals, what did I say? So I get 100 equals I1 times 32, what would be 32 minus J8 plus V1. In fact, I'm gonna write that a little bit differently here. I'll write that as V1 plus I1 times 32 plus J8, like that, or minus J8. Sorry, 32 minus J8 was what we had over here. And then for the other one, I have negative 20 angle 20 degrees is equal to V1 over 4 plus, or sorry, minus I1 times 4 times what? 3 plus J2. Okay. So how do I solve this? Well, basically for me, I turn this into matrix form. I say 100 and then minus 20 angle 20 degrees is equal to 132 minus J8, 1/4, and minus 4 times 3 plus J2, all times V1 I1 like that. So when I solve this, I'm going to get my primary side voltage and my primary side current, from that solution. And then what do? Well, what else did I say that we wanted to find in this case? So back at the beginning, I was saying, well, we also want to get the secondary side stuff. So how would I get that? Once I went and turned the crank on this and got V1 and I1, what would be the next step to get the other two, to get the other voltage and the other current? What would I have to do to get those? You guys can turn your mics off.
So you said you want to find the V1 and I1?
Well, so once I turned the crank on this, I could solve. I'd solve for V1 and I1, right? Once I have V1 and I1, how would I get V2 and I2?
You get V2 with just V1 over 4.
Yep. Yeah, so V2 is simply V1 over 4, right? So I would just take that phasor and basically divide it by 4. So there'd be no change in the angle, right? I'd be changing its magnitude by dividing by 4, right? And then I2, oops. Hang on. What did I just do here? Let me go back to my current slide. Okay, sorry. I2, we'd use the same sort of relationship. I2 is negative 4 times I1. Right? And I would end up getting the current on the secondary side, right? So that would get us to sort of the right result, right? That's the basic set of steps for any of these problems. You guys with me there? Questions about that process?
Yeah, so I don't get why you bring the V2 and I2 equation. So should that come like after we find V1 and I1?
Yeah, once you find V1 and I1, you then take those results and you plop them into here.
Oh, all right. Yeah. So that's the next step.
That's the next step. Yeah. All right. So let's take another example. Same thing, right? So different circuit, but I want to find V1, V2, I1, and I2. All right. And I'm going to go through the same steps. All right. So the first step was to get the voltage relationship. All right. So for whatever reason, I don't know, I guess I like these things with 4-to-1 turns ratios, but how do I approach this guy here? First step on the voltage relationship. How would I write the voltage relationship in this particular case?
You'd have V1 over N1 is equal to negative V2 over N2.
That's correct. Yeah. So V1 over N1 would be V1 over 4 is equal to negative V2 in this case. All right. And I guess these are phasors. I should be putting a bar there, right? And the reason it's negative is because the plus sign is at the dot on the left side, and the plus sign is away from the dot on the other side. So that gives us a negative. Okay. So that's the first step. I've got a negative that's been defined in this particular instance. All right. Now, the next step for me basically is to get the power relationship. All right. So again, our basic approach is that P1 plus P2 equals 0. All right. So I got to write P1 and P2. So P1, how would I write that in terms of the way I1 is defined? So to be clear, I1 is going this way. Oops. I1 is going this way, as it's been shown. And I2 is going that way, as it's being shown. Okay. So how would I write P1 here?
Positive I1 V1.
Yep, positive V1 I1. What about P2?
Same thing, but negative.
Yeah, this would be negative. Now, why negative?
Because it's going into the negative terminal.
Yeah, so it's basically, yeah, the arrow's coming out of the positive terminal or into the minus terminal, so that becomes a negative. So basically what I get is that P1 plus P2 is V1 I1 minus V2 I2 equals 0. That's really kind of our second step. The third step is to take that and turn it into a current relationship. So I'll start it here and say, well, I got V1 I1 minus V2 I2 equals 0. And the voltage relationship that we had defined previously was that V1 over 4 equals negative V2. Make that a 4 somehow. Close enough. All right. So V1 over 4 equals negative V2. So what do? I basically substitute that in for V2. So that turns this into V1 I1. So I plug that in over here. V1 over 4 plus V1 over 4 times I2 is equal to 0. It does not want me to make a 4. All right. All right. So what do? I basically factor out the V1 from both sides. And I end up with the fact that I1 equals negative I2 over 4. So now I have my two key relationships. I got my voltage relationship, and I got my current relationship. So I can clearly see here that the voltage is got to be higher on the primary, and the current has to be higher on the secondary. I say higher because I2 is 4 times I1, V1 is 4 times V2. That's where the higher is coming from. Okay. Questions about how I got through that process right there? Okay. All right. It gets us to the last step, which is basically to solve and to figure out, what the voltages and currents are. All right. So in this particular case, let's do that. So let's call this guy again. I'm going to say I got VA right here. VA is the voltage across the 18 and the negative J4. And then I'm going to say VB is the voltage across the 2 plus J1 in series with each other. Okay. All right. So if I go through that process here, all right, what am I going to end up with ultimately? I am going to end up with, let's see, so let's do the left mesh. Again, I'll start here, right? So I'm going to say 0 equals, and then I go around in the clockwise direction. So somebody help me out. How do I write the KVL around the left mesh?
Negative voltage source plus VA plus V1.
Yep. So it'd be negative 120, angle 0, but I'm not writing that here. So plus VA plus V1. So I'd say 120 equals, and I'd substitute in for VA. VA would be I1 times 18 minus J4 plus V1. Okay. And again, I'm going to write that as V1 plus I1 18 minus J4. So that's one equation. Now I'm going to do the same thing again for the secondary, and then I'm going to use those relationships for the current and voltage to get this equation into just being two unknowns. Okay. So what do I do on the other side? Well, I say 0 equals, and so I go minus to plus on V2. So I say minus V2 plus VB. So minus V2. And so what's VB? Well, I have a current I2 flowing into this plus terminal. So I would say plus I2 times 2 plus J. What do I do at that point? I've got two equations and 4 unknowns. How do I get it back into just 2 equations?
Use the relationships you found earlier.
Yep, I use my relationships. So my voltage relationship is V1 over 4 is negative V2. So this guy becomes V1 over 4. And then this guy here is, let's see, plus I2. What do I do with the I2? The I2 is equal to negative 4 I1. So I would say this becomes negative 4 times 2 plus J times I1. Now I have two equations and two unknowns, and I can solve that properly, right? So in this case, if I go through that process of trying to solve those, let me see. What do I end up with? I have them written down here, but I'm not sure that I have them. Let me and write the angle down for one of them, right? So let's just make sure we can follow the process here. So let me go to MATLAB real quick. Yeah. All right. So I set up basically this particular system, all right, in MATLAB right here. All right, here's how I did it. So if I move this to the side, you can see I've got two equations here, right? The first one, 120 equals, this is the V1 term. Let me write it. Well, I'm gonna mess it up if I do this. The first coefficient here, this is the first row. The first coefficient is the V1 term. The second coefficient, the 18 minus J4, that's the I1 term. And then on the bottom side, I have V1 over 4. So that's the 1/4 that I have right here. And then the minus 4 plus 2J. So what I do is I solve that. So I'm going to take that real quick and I evaluate that. And then I can look in the MATLAB command window to see what my results were. All right, so I see that X was my result. So if I look at this and I say, what's the abs of X? That's going to tell me the magnitude of V1 and the magnitude of I1. And so I do, what I'm going to do to get the angle is I say angle of X, and I want it in degrees. So I do 180 over pi. So I get that. So 13 degrees for the voltage and negative 13.5 for the current. So basically what I end up with here is I end up saying that V1 equals 83.494 angle 13 degrees. And then I1 is basically 2.33 angle negative 13.5. So if I then want to figure out V2 and I2, I basically just go through my process. So V2 was supposedly equal to negative V1 over 4. All right. So I basically plug this into this equation. And what do I end up with? I'm going to end up with 20.87 for my magnitude. Without doing any work, what's the angle going to be?
13.
What is it?
13. The same angle, right?
Well, so there's a minus sign there, right? So it would end up, what would that change, that minus sign? What does it
It's gonna be
mean?
180, I think.
So when I'm multiplying complex numbers, so basically it's like what I have here is minus 1 times basically 20.87 angle 13 degrees. So I need to, when I'm multiplying complex numbers, I add their angles, right? So what's the angle of -1? I think you said it, there's 180, right? So I add their angles. So what's this? Yeah, it's supposed to be 193, right? 193 degrees. And then similarly, if I did this for I2, I'm going to get a similar effect. I2 is going to be a bigger current. So this is 2.33. This guy works out to basically be 9.33. And the angle in this particular case would work out to be negative 193.5. And you could look at the same approach in doing this to get the negative 193.5. Some of you guys might look at that and say, well, shouldn't it actually be 166.5? 166.5 and negative 193.5 is the same, isn't it? How can I tell that? How could I tell that? No ideas? If you graph them, right, basically, so I mean, they're equivalent angles, right? If you graphed, essentially negative 180 and 180 are the same. So if you went through the process and said, okay, add negative 180 to negative 13.5, you'd get what I got there. If you did 180 and added it to negative 13.5, those are two equivalent operations. That kind of complex number thinking is something you guys should be comfortable with from 2254. If you're not, you should get there. All right. Anyhow, all right. That's about it with respect to transformers. They're fairly straightforward. This is about the level of difficulty with problems that I would expect to do, and you'll have some on the next homework. Now we're going to use a lot of these in a lot of our power problems. And so I'm going to take the last couple of minutes here to introduce some things around single phase electric power, and then we're going to get to some problems associated with single phase electric power on Wednesday. All right, so something we talked about already here in this lecture is we talked about this kind of what is the definition of power. So what is the definition of power? Well, it's the rate at which energy is absorbed or sourced by an element. And so what does that mean? If I say it's the rate at which energy is absorbed or sourced by an element, the definition of power is that it's the rate of change of energy. And we usually write that like this. I'm writing a partial derivative, not to say that we're going to do partial derivatives, but that's what this is, where W is work, and work and energy are the same thing. So power, sometimes we use power and energy interchangeably, and we really shouldn't. Power is the rate at which we're using energy. So an example would be when I have batteries, grid scale batteries. Sometimes we say it has a rating of 1 megawatt and 4 megawatt hours. So 4 megawatt hours is how much energy I could get out of that thing if I discharged it, if I used the energy at a rate of 1 megawatt. So I don't want to say too much on that, but basically for our purposes, basically this works out to be V of t times I of t, right? V of t times I of t in an electrical standpoint. An important thing here is if that P is greater than 0, the element that we've got is absorbing energy. If it's less than 0, it's sourcing energy. That gets a little bit weird in the context of AC systems, and that's kind of what we need to talk about a little bit. Question is, what's V of t times I of t going to look like, right? Let's say I had a 100-watt light bulb connected to a 120-volt source, right? If it was DC here, right, what would the current be in this particular case? How would I figure out the power and the current? How would you calculate the current if that was a 100-watt light bulb and that was a 120-volt DC source?
100 over 120?
Well, so if it's power, right, you would say the power is equal to the voltage squared divided by the resistance, and V times I like that, right? So yeah, I think exactly what you just said. 100 divided by 120 would be the current. That should work out to be about 0.833 amps if I do that math, okay? Pretty straightforward to do the calculation in this particular case. Now, if I did this in the context, though, of a AC system, what I would get in this particular case is the power is equal to V times I. And if I applied a voltage that was basically V peak cosine omega t, right? And let's say that omega was such that the frequency was 60 hertz, I of t would basically end up being, I'm not sure exactly what its amplitude is going to be. I know it's going to be, I think it's roughly going to be square root of 2 times 0.833, but I don't particularly care what the amplitude is. I looked at a graph right here. What you guys should know is that the current and the voltage would be in phase with each other. So here is my voltage here. This is the 169 cosine 2 pi 60 t. That's what this is here that I've drawn on the top. On the bottom, or I guess in the middle, what I have is the current, all right? So they should be aligned with each other. There's no phase shift if I'm applying a voltage like that across a resistor, okay? If I do V of t times I of t, the result is what's shown at the bottom. Now, where the heck is the 100 watts? Where does that show up here when I multiply those two things? So when I look at the power, this is a 100-watt light bulb. You got those, I guess anymore, you don't have them as much in your house because we've gone to LEDs and whatnot. But if I had a 100-watt incandescent light bulb like that, or even if I had a 10-watt light bulb like you might have nowadays, where's that number 100 coming into the picture here? Where do you even see that? If you look at the power, P of t times I of t. So the power's at the bottom, right? So what I did was I drew these two red lines, basically show me one period, right? And I see right in the middle there is the number 100. What would I say that corresponds to in looking at a waveform like that? This is just a math problem, and I said there's a waveform and there's the number 100 going through the middle of it. What would I call the number 100 in this particular case? Mathematically. So it's the center of that waveform. What should the center of that waveform be called from a math perspective? Anybody? Somebody has an idea. It's the average of it, right? If I look at this waveform right here, right? So the waveform on the bottom. So Ike, thanks for stepping up to say something on me, right? Looking at this, like what I see here is that the average value of that power waveform, the average value of this, the bottom is 0, the top is 200, 100 is right in the middle. It's the average value of it. So what we say is if I did this out mathematically, right, is that if I do P of t, which is V times I, it would be V times I peak times cosine squared, which basically becomes this. If I took the average of that waveform, the average would be this number right here. For this particular light bulb, that would work out to be 100, but the number would be 100, it'd be 100 watts, okay? What we do is, in looking at this, I computed the average. What we do is we use the definition of average. We take that P of t, and we use the definition of an average to basically say we integrate over one period and divide by the length of that period. Looking at this, we say that the average value of the power waveform that we have, the average value of that, looking at this graphically, is right there in the center. It's the number 100. Now, we're not going to do this calculus, right? But we're basically going to use the results of this calculus. And what we're going to do is we're going to say, okay, well, that number 100 watts basically is the average power, because it's tricky to define one number when it comes to the power of an AC load, right? Because looking at this, the power, if it's V times I, is basically this kind of cosine that's going up and down. And if you look at it, it actually has twice the frequency of either the voltage or the current. So it's very confusing. There's a lot of different numbers that I could use. Technically, there's infinitely many numbers between 0 and 200 that I could use to describe it. So what we use is we say, what is the average power that is absorbed by that load? That average power is 100 watts. That can be very carefully related to the peak values or the RMS values of the two waveforms, the current and the voltage. That is what we'll talk about in detail on Wednesday. I'm going to stop there. Any questions from you guys?
I had a question about the